Okay, ladies, today, let me have your attention. Y'all can pick those materials up unless you have a question, and you can keep that paper copy of your problems. Those of them that are absent, I'll give those to them tomorrow. So I will be closing out the Moodle test, though, so that you won't have access to it after today. So, any questions? Everybody was good on the Moodle items that you missed or did not miss and just guessed on, and you understand them, could explain why? Yes? Mm-hmm. Who said that? Mm-hmm. No, inward is the right answer. Maybe you said it was outward and it should have been inward. Okay? Because the clothes in a spin cycle of a washing machine would be kept in circular motion by the normal force from the drum. That's just, you know. Very similar, yes. Let me point out to you also about washing machines. Have you looked inside the tub of a washing machine? It's a big old tub with lots of holes in it, right? Yes? And so basically those holes are there, and they are of a certain size, not very large. Large enough for water to go through, but not large enough for clothes to go through. Which is why sometimes if you take shoelaces out of a shoe and put them in a washing machine, you'll lose them. They won't be there when you open the washing machine because they're small enough to get through the hole. Does that make sense? So if you have small items, this is your homemaking tip of the day. If you have small items that you want to wash in the machine, you need one of those little mesh bags that you put things in, like your pantyhose or stockings or real delicate things. You might want to put them in one of those also so that they don't get quite as much abuse in the washing machine. But the idea of a washing machine, the tub, the holes are not big enough for the clothes to go through, so the normal force keeps them pushing in, and yet the water is small enough that when it's over the hole, it can go through. And so that's why, you know, the first time around, all the water's not going to get out, but eventually through the spin cycle, the water gets out. And if you stop it before the spin cycle is over, the clothes are still damp because not as much of the water has been slung out. And of course, that's not centrifugal force pushing the water out. It's the water's inertia wanting to keep going straight, and the tub turns in front of it, so it's got to go through the holes. All right. One other homemaking tip of the day, which I was amazed to find out how many, not actually so young, teachers didn't even realize. When you put clothes from the washing machine into the dryer, in chemistry, didn't you learn that you get more effect when things are larger surface areas? Which is why when you remove the clothes from the washing machine to put them in the dryer, you should shake them out and then put them in the dryer. If you take a towel right out of the washing machine after the spin cycle, it's all wadded up and squished together. You throw that in the dryer, you're going to use more electricity or more gas, if you have a gas dryer, to dry that towel than if you just simply shook it out. So in order to be good stewards of the resources of the earth and of your pocketbook, you should do that. It doesn't take that long. That's one of those mindless things. When you become a mom and you're doing the washing, nobody bothers you then much. So you can just kind of go in there and make out like you're doing, just take your time and throw them in. That and cleaning bathrooms. Nobody bothers you when you're cleaning the bathroom. Exactly. Their fear that they may receive the sponge. Yes. Only thing is you go back 15 minutes later and it's already messed up. Okay. Today's activity, y'all are going to work in groups, and I'll tell you about that in just a minute. That group work, you're going to go through those pages that you had assigned to read and go through. If you've read through those, you'll notice that those problems are all so the problems that you did the other night for homework. So I would suggest that you go through the ones quickly, not necessarily showing all the work like you have to on a test, but just to make sure that you know how to do it and so forth, particularly those where it just talks about if this mass is doubled and that one is cut in half, because that was probably the thing that more people missed on that little worksheet the other night than anything else. And before I go any further, is there anyone who's still the least bit shaky on using their calculator with the universal gravitation law problems? Everybody's got that. Okay. Now, those 3 pages from physics classroom that you're going to be reading, basically you're going to get in your group and y'all are going to write a summary of the information, and that doesn't mean copying and pasting. That means read the section and summarize in your own words, okay? Because I think that's one way that'll help you. But before you do that, I wanted to give you a little bit of pre-information on satellite motion, because that's what we're going to be focusing on coming up. So satellite motion. Now, we're going to be talking about satellites around the Earth, because we're Earthlings. But the same physics and mathematics principles are going to apply if you had a spaceship that you had sent up to Mars and is now orbiting Mars, because we do have that. There is an orbiter around Mars now, and the rovers send the signal to that, and then it boosts the signal back to the Earth. So you certainly can have satellites around other things, and any planet that has a moon has a satellite around it. So, and the same principles are going to hold. Of course, instead of using the mass of the Earth in your calculation, you'd use the mass of that particular planet and so forth. But the principles stay the same. So one thing I wanted to talk to you about that always, I don't know, it's the simplest part of it, and it confuses people. If you have the Earth or any planet, and this is the radius, and I'm just going to say planet X, okay? It could be Earth, it could be Mars, it could be whatever. That's the radius of the planet. And then this is the orbit of the satellite. And if I say that this is the altitude, can't spell today, altitude of that orbit. Altitude is the distance above the planet's surface, okay? Altitude is the distance above the planet's surface. But what you're going to be interested in using for the calculations is actually going to be this distance, the orbital radius. And I think you can all agree that the orbital radius is going to be the sum of the radius of the planet plus whatever the altitude is. Does that make sense? Just looking at the picture. Okay? So the radial orbit, radius of the orbit, is equal to the radius of the planet plus the altitude of the orbit above the surface of the planet. Now, when we put satellites up in orbit, we want them above the atmosphere so there's no air resistance slowing it down. But there's still a few little bits of air, regardless, floating about out there that's going to slow it down some, which is why Satellites usually have little small rocket boosters built into them so that when the orbit begins to deteriorate, as it starts to slow down a little bit, it can shoot a little out and speed itself up a little bit. And when all that runs out, then eventually the satellite ends up crashing back to Earth because it gets to going too slow. Now, when we look at something that's in orbit, if it's in a fairly low Earth orbit, the altitude generally is not really that significant a difference, though certainly if you were a rocket scientist, you'd have to take it into consideration. But you'll often find that by the time we work problems and round off for sig figs, the answer is the same. So, but you do need to account for it. So let's see. All right, a satellite in orbit is showing circular motion, right? So what kind of forces produce circular motion? Centripetal forces, right? So we know that there is a centripetal force acting on the satellite in order to keep it in motion, in circular motion. And the formula for centripetal force is mass, and in this case, it's the mass of the satellite, m, v squared over r. And what r would that be? Would it be the radius of the Earth or the radius of the orbit if you're talking about keeping the satellite in this circular path? Orbit, okay? And since you have so many of these radii that you're talking about, it's going to be important that you identify what you're talking about. Okay. What is it that provides the centripetal force and keeps that satellite from just flying off in a straight line path in accordance with the law of inertia? Gravity. And we know the formula for the gravitational force is big G, and remember that G can either be written out in front or in the numerator. It means the same thing. Mass of the satellite times the mass of the Earth or the planet, whatever it's orbiting, divided by the distance between their centers, which again is the orbital radius, but that has to be squared, and don't forget the square. Okay? So this centripetal force is provided by the gravitational force, so those two things are equal. That's what's providing it. And therefore, I can say that the mass of the satellite times its velocity squared divided by the radius of the orbit is equal to the gravitational constant times the mass of the satellite times the mass of, I'm just going to put capital E for Earth, over the orbital radius squared. Now, when I look at that, it's quite obvious that we have two things that are the same on both sides, the mass of the satellite and the radius of the orbit. So I can cross out this and this, and the square. So I end up with v squared equals G, big G, the constant, times the mass of the Earth, or whatever planet you're dealing with, over the orbital radius. Now, the significant thing to realize here is the mass of the satellite has nothing to do with how fast it has to be going to maintain that orbit. That's the key point there. Every object orbiting at that radial distance must maintain the same speed. Now, when you stop and think about it, if you have more than one satellite orbiting in the same orbit, it's a very good thing that everything's going the same speed, right? Because if not, one of them would be running into the other one. If they weren't going the same speed, eventually they'd run into each other. So, all right. So now we can see, and if you wanted to, we could say V equals the square root of G times the mass of the planet divided by the orbital radius. And notice the square root is over the whole thing, so you get your answer and then take the square root. Or square root and put everything in parentheses. So the key point there is that the mass of the satellite really doesn't matter. Now, when you look at that, G is a constant. Obviously, it doesn't change. The mass of the Earth is not going to change. The only thing that changes there would be the radial orbit. So really and truly, the only variable that affects the orbital speed, the tangential velocity, is how high up it is. Does that make sense? Now, the higher up you go, what happens when the radius increases? The speed decreases. Notice that? The speed decreases. But it decreases by the square root factor. So if I have twice the orbital radius, if I double the orbital radius, my speed is going to decrease, in other words, be divided by not 2, but the square root of 2, 1.414. Does that make sense? Okay. If it had been in the numerator, then you would have multiplied it by that. But because it's in the denominator, if my orbital radius increases, my speed decreases by the square root of that factor. And that's purely from this formula here. Now, does that make sense to you intuitively? Wouldn't it make sense that you're going to have to go faster close to the Earth in order to keep missing the Earth? If you're way up here, you don't have to go as fast to keep away from hitting it. Does that make sense? Intuitively, it seems to me that it does. I don't know, and you need to kind of ponder upon that some and see that it makes sense to you. That has something to do with it, yes, but also just and that's basically where the F-grav came in. And you've got a tighter circle. Yeah, does that make sense? Yeah, the smaller the circle, the tighter it is, so you've got to go faster to keep it up, right? Like if you take something, let me get my hand. This is one of the most useful visual aids I've ever come up with. A weight on a string, huh? If I get something going around in a circle, I just don't want to let go of it. I bet you don't either, huh? Okay. If I get this going around in a circular path, I don't know if this is going to work. Let's see. Nope. I need one of those straws. Let me see. No, I don't have time to do it. I'll show you that another time. But if you have something going around on a circle and you pull it down where it shortens it, it goes faster and faster. Okay, so that being said, now another very, very important orbit is what we call geosynchronous orbits. Geosynchronous. thought about how to spell this. G-O. Somebody help me. Synchronous. I think that's right. Somebody look that up. When I was in first grade, we didn't do phonics. We just memorized the words. I was so mad in the third grade when somebody pointed out that you could sound out the word. And I'm thinking, you mean they have had me memorizing every word I saw for all these years for no good reason? How stupid was that? And then when my little children were watching Electric Company, I learned about the silent E and all these phonics things. I said, gee, somebody should have taught me that. You know, they go through all those weird changes in how they teach reading. All right, geosynchronous orbit. Is that the right spelling or not? Okay. Yeah, because you have to look at the next one over and see whether you're going to be carrying or not. I once taught remedial general math, and they would always ask me if I wanted them to do it my way or the easy way. And the easy way was if you had 52 minus 27. 2 from 7 is 5, 2 from 5 is 3, and there's your answer, which is wrong. But you didn't have to follow. I'll say this for you, ladies. When you have your babies, read up on the Montessori methods. Montessori methods are excellent. They were developed for teaching mentally delayed students, but but like 3 different families are doing that, and the kids are smart. Yeah. Help with their homework, and they do really well. Yeah, they pick them when you're ready to start reading. Doesn't matter what age you are. When you're ready, that's when you do it. And they got all these different ages doing it. It's really a great method. Anyway, but that's besides the point. Geosynchronous orbit, synchronized. In other words, when you talk about a geosynchronous orbit, it means that your satellite is always above the same point on Earth. In other words, it has the same period as the Earth's period, which is, of course, 24 hours. What's an application that you can think of that would be very important to have a geosynchronous orbit? Satellites that are used for communication, that sort of thing? Yeah? Yes? Makes sense? Okay. So some satellites are not in geosynchronous orbits and some are. All right? And if you think about it, it simply means that the period of the satellite is equal to the period of the Earth, which is 24 hours. 24 hours is how many seconds? What are you going to have to multiply by? 24 hours. Let's see. 24 hours, 1 hour, 60 minutes, 1 minute, 60 seconds. So pick up that calculator and tell me how many seconds you have. $86,400. $86,400 seconds. That has to be the period. am I going with this? Okay, I know what the period is. What do I really want to know about the satellite if it's going to be in a geosynchronous orbit? What defines the orbit? No, what determines where your orbit is? It's what? The distance, the radius, huh? Okay? So, I am, because I have to. I can't see it. I just need another page. All right. So if I know the period of the satellite is 86,400 seconds, let's see. V, I haven't done this recently, so we're on an adventure together right now. But that's what makes teaching more interesting. You know, some teachers don't do that because they fear looking foolish in front of their class, but I abandoned that notion long ago. So we know that the speed of the satellite is equal to 2 pi r, and that would be the orbit, right? The orbital radius, 2 pi r, that's the circumference of the circle, divided by the period. We also know, oh, glad I just thought about that the speed of the orbit is equal to the square root of g times the mass of the Earth divided by the orbit, yes? And so, if A is equal to B and B is equal to C, then A is equal to C. So we can set those two equal, right? What are we doing right now? We're playing math. We're just messing around with math, taking some algebra stuff and stirring it together and see what we can come up with. So, I've got 2 pi times the orbital radius. I know pi. I know the period. I'm just going to leave it t for now because it's too many digits to write out, okay? Equals the square root of g, mass of the Earth, over the orbital radius. Well, I see orbital radius on both sides, but one of them's under a root, so maybe we ought to square everything. When I square, am I moving it up too far? Is everybody with me? Let me know if I need to lower things. So that's going to be 4 pi squared radius of the orbit squared. I'm going to put it in parentheses, not that it really needs to be, but just to keep it together, over t squared equals g times the mass of the Earth over the orbital radius. Then I guess we need to cross multiply maybe. And I get 4 pi squared radius of the orbit squared times the radius of the orbit. I'm going to go ahead and write it out. I probably would have just written it cubed, but just so that you can see what's going on. That times that. This times this. G, mass of the Earth, times the period squared. And so this would be the radius of the orbit cubed. And so when I divide, I've got r of the orbit cubed is equal to g times the mass of the Earth over t squared divided by 4 pi squared. And so how do I find the radius of the orbit? Cube root is equal to the cube root of g, mass of the Earth, t squared over 4 pi squared. You know g. You can look up the mass of the Earth. We already know what the period is, 86,400 seconds. And certainly you know 4 and pi. We just did some rocket science. So if I want a satellite to be in a geosynchronous orbit, I know that this is the distance it needs to be. Now your task is fill this in. The mass of the Earth is, I'm sure a book has that information without having to Google it. Let's see. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And the radius of the Earth is 6.37 e to the 6th meters. Now I'm going to mention what that radius is because we're calculating the orbital radius. Basically, what you really want to know is how high above the Earth you need to get it. So what are you going to have to do after you find the orbital radius? Subtract the radius of the Earth to get the altitude, huh? Put that in your calculator and see what you come up with. I'm so glad that worked out well for us. Now, when y'all start reading about the satellite motion in physics classroom, it should make sense to you. And I guess we didn't get to that group activity yet, but we're going to do that tomorrow. Okay, well, where are you going tomorrow? Oh, that's choir tomorrow. Where is it y'all are going? There was something kind of, why are y'all going to Ambrosia? Are you free 2nd or 7th hour? All right, once you get an answer there, let me know. I'm going to work out what my units are because I'm kind of interested in that. When I take my units, Well, that looks really strange, doesn't it? But let's see. I know that a Newton is a kilogram meter per second squared times meter square times second squared divided by kilograms. Oh, well, my kilograms go away. That's nice, because I don't want that for sure. Oh, and then my second squares cancel out. Oh, and then I'm left with cube meters. Oh, I love math. It's so nice the way it all works out. Why does that bring joy to my heart when I see things like that? Do y'all get the appreciation of how that works? I mean, that doesn't... What'd you get? For the orbital radius. The orbital radius. What did you get? Okay, has anybody gotten this answer? All right, what did you get? Put in scientific notation. 4 point, did you take the cube root? Okay, cube root. All right, and what did you get? All right, let's put 3 sig figs. 4.2 who? 2, 3? All right, now, are you ready? Over here, you got some more math to do. Our orbit is 4.2, so I'll write 3, 4.23 E7 meters. The radius of the Earth is 6.37 E6. Meters. Okay? So if I want to know my altitude, it's going to be 4.23 E7 minus 6.37 E6 meters. Now, leave your calculator alone and look up here. Let's think a little math. This is 10 to the 7th. This is 10 to the 6th. You need to get those decimal places lined up for it to work. So 6.37 E6 is exactly the same thing as 0.637 E to the 7th. Does that make sense? If I move it 6 places to the right from here, or if I move it 7 places from the right to the right from here, you get the same number. Okay? So if God hadn't given you that calculator, could you do it by hand? Yes, you can. And to do it by hand, you would have 4.23 E7 meters minus 0.637 E7 meters, and I get E7 meters, and when I subtract, I'm going to get, what, 3.6? 3.9? 5.9? All right, but we'll just call it that. That's the altitude. That's how high above the earth it needs to go to stay in a geosynchronous orbit. Well, let me ask you this. Does the period of the Earth change? No, it doesn't. And remember, that was what you want. To make it geosynchronous, you had to have that 24-hour. And so everything else is driven by that and constants. Well, that you can think of it as a constant that every geosynchronous orbit is going to have that altitude, yeah. Now go back, take a minute, go back through all that, because that was a lot of math we just kind of quickly went through. Up, down. I'm sorry? This? Yeah, that's what I looked up in the book. And I don't expect y'all to memorize those things. If you did enough, if you were a rocket scientist, you would have memorized it by now. But we're just going to be temporary rocket scientists. Steely-eyed rocket scientists. I think I am going to show y'all Apollo 13. There's so much physics in that. I hadn't watched it in years and years now, so I think I can watch it again. Huh? Down? I've started to put my finger up there and scroll. You know, going from this to the computer. And girls, today at lunch, we're going to put the computers that are up for consideration on the teacher's table in the cafeteria. So if you'd like to go and see and kind of voice your opinion of what you like or not like, you can do it there. All right, so tomorrow's class, listen to me. Listen to me. You didn't have any turn-in homework last night. You don't have any turn-in homework tonight. But you do need, as an individual, go through the rest of those 3 pages on Physics Classroom. Tomorrow, you're going to have about 20 minutes class time to get with your group and summarize that information. So don't be a parasite and not come prepared. You can do the same thing. Yeah. Right, let me shut this off.